Okay, guys, today we're going to introduce a very important concept in fluid, which is buoyancy. So what is buoyancy? Buoyancy is the upward force of a liquid. It's generated by liquid. The liquid could be fluid. Actually, it's not only for liquid, actually. Even in gas, we still have buoyancy force, and we'll introduce the buoyancy force in the gas later. But now let's start it from liquid. So if we look at, let's say, this cylinder block in a container of water or any other liquid, we can imagine that the pressure in the liquid increases with depth. This is what we have learned previously about the pressure. Pressure could be calculated by, if you remember the equation, it's rho g h or rho g d, the depth. So if we compare the pressure at the top and the pressure at the bottom of the cylinder, we will notice that the pressure on the top should be less than the pressure at the bottom. The same thing for the force, because force equals to pressure times area, right? So if the pressure at the bottom is stronger, then the force at the bottom is stronger. And now let's talk about the direction of the forces on the top and at the bottom. On the top, the force is going down, which is trying to push the block down. And at the bottom, the force is going up, which is pushing the block up. Now we notice there's a difference between the force pushing up and the force pushing down. And the net force could be calculated using this equation on the corner. The net force equals to the force up subtracted by force down. And then this force net is the equation for net upward force, or we can call it buoyancy force in liquid or gas. And this is very natural. And it happens for any liquid and any object. Imagine you put any object in any liquid, because your object will have a volume. So there's always a force pushing down and force pushing up generated by the liquid and exerted on your object. And this net force can always be calculated by subtracting force up and force down, and then you get the net force, which is a buoyancy force. But this is very common in daily life, but how to calculate it, this is what we're going to learn in this class. So first, this is very common. For example, if you jump into the, let's say, swimming pool, you will feel you get lighter simply because any object, including human body, if you're immersed in the water or any other liquid, the buoyancy force happens, and the net force will push you up. That's why you feel it's lighter when you're in the water. But how to calculate it? Let's see. This is a way to calculate buoyancy force quantitatively. Now, if an isolated parcel of a fluid is in static equilibrium, then the parcel's weight, pulling it down, must equal to the upward force or the buoyancy force. Let's look at the image A or figure A. This is a container containing fluid. Let's say it's a container of water. So it's purely water, nothing else. And the dashed line gives you an ideal experiment. Now, let's say the dashed line or the dash surface gives you a part of the water or a parcel of water. You can imagine um, the part of water is wrapped by some plastic wrap or something, or even there's no any plastic wrap. It's wrapped by water itself. So if we consider this part of water, if we do the free body diagram, or if we analyze the forces for this part of water, you will see first there's a weight of this part of water, and then there's a buoyancy force. The weight is going down, buoyancy force is going up, and this part of water doesn't move. It doesn't go up or go down. That means the buoyancy force equals to the weight. Okay, so after this experiment, you can imagine that a more general rule is the buoyancy force matches the fluid weight. Or we can say for the fluid itself, buoyancy force equals to the weight. Now, imagine that you changed or you replaced this part of fluid or water into another object, let's say a rock or a wood, a piece of wood or something, a block, which has the same, let's say, exactly the same shape of the previous part of water, and then you put it in the container, which is full of water or fluid, then what's the buoyancy force? If we replace the parcel of liquid with an object of the same shape and size, the buoyant force on the new object is exactly the same as before. Does that make sense? You can imagine. So in the first experiment, we imagine there's a part of block, but this block is, or this object is built by water. So it's water object. And in this case, we can calculate the buoyant force for this part of water. And now we don't do anything change for the liquid. The only thing change is we replace this water block into, let's say, a wood block or any other material which has the same size and same shape. So you can imagine they should have, if they have the same shape, exactly the same, then they should have exactly the same buoyant force. And the way calculating the buoyant force on, let's say, this wood object is already derived in the previous experiment. It equals to a weight of water. And then if you agree with this experiment, or if you understand this, then we can get a conclusion of how to calculate the buoyancy force. When an object is immersed in a fluid, it displaces the fluid that would otherwise fill that region of space. This fluid is called displaced fluid. And Archimedes' principle. Archimedes is a scientist, let's say, in many years ago. So he already found the way to calculate buoyancy or buoyant force during his time. And we named this calculation to be his principle. So Archimedes' principle. It states that a fluid exerts an upward buoyant force on object immersed in are floating on the fluid. The magnitude of the buoyant force equals to the weight of the fluid displaced by the object. So this is a way of calculating the buoyancy. If we write this principle in equation, it should be buoyant force equals to rho fluid times V fluid times G. So G is a constant, gravity constant. V is the volume of displaced fluid. Rho is the density of the fluid. So it's a very simple calculation. If we go back to the previous experiment, how to calculate the weight here, the weight of fluid? Let me write it down quickly. If you want to calculate the weight, it equals to, do you remember? mg. Weight equals to mg, right? M is a mass. Mass equals to rho v. Rho is a density, v is a volume, g. Rho is the density of fluid, and volume is the density of fluid, or more accurate, V is the volume of the displaced volume of fluid. And then you can calculate the weight, and the weight equals to Fp, which is a buoyant force. This is what we derived in here. And this equation is exactly the argument's principal equation. I'll clear the drawing, and now let's go forward. So it's exactly the same here. This is the way of calculating the buoyant force. Okay, so we have introduced the most important thing today, buoyant force. Buoyant force will be in your exams for sure. It's one of the most important thing we learned in this whole course. So please remember this equation, and you need to use it many times. Now let's see some examples. A heavy lead block and a light aluminum block of equal size are both submerged in water, upon which is the buoyant force greater. So which one is greater? Please type it in chat and let me see your answer. So which one is greater? Do you have your answer? If you have your answer, please let me know in chat. Okay, now let's see the correct answer. They're the same. The buoyant force are the same because the buoyant force can be calculated by rho v g. So rho is the density of, in this case, water. G is a constant. The only thing matter is v. And we said it has equal sizes, means v is also the same. So no matter it's a lead or aluminum, they have the same buoyant force. Two blocks are of identical size. One is lead and sit on the bottom of pond. The other is wood and floats on top. Which buoyant force is greater? Please think about it and show me your answer in the chat. Now let's see. The correct answer is A. Because the fully submerged lead block displaces much more water than the wood block. Because a wood block is on top, so only part of the volume of the wood block displaces water. But for lead, it's in the bottom. So the whole size or the whole volume of the lead block displaces water. So the displaced water is greater in the case of lead block than the buoyant force is greater. Okay, now a barge filled with ore flows in a canal lock. If the ore is tossed overboard into the lock, the water level in the lock will. Okay, you'll figure out. I'll leave this to you to think about it later after the class. Let's move forward to a more complicated example. Legend has it that Archimedes was asked by the king to determine whether a crown was pure gold or had been mixtured by some other metal by some smiths. So it's complicated because imagine now it's a crown. It's a complicated shape. If it's let's say a cube or a regular shape for a piece of gold or metal, it's easier to determine if it's pure gold or not, based on the size and the weight. Then you can calculate the density. If the density is not the same as gold, then means there's some other metals mixed into the piece of metal. But now the crown, you can imagine it's a very complicated shape. It's difficult to measure the volume. Then it was this problem that led him to the principle that bears his name. Now here is a modern version of his method. Now a crown with 8.3 Newton is suspended underwater from a string. The tension of the string is 7.8 Newton. Is the crown pure gold? Now, if you only have those two numbers, the weight of the crown and then the tension of the crown when it is submerged in water, can you calculate if the crown is gold? The answer is, of course, yes, there's a way. So first of all, how to identify a crown is gold or not, or pure gold or a mixture of gold and other metal? The key is density, actually, because gold has a very large number of density compared to other metals. So if the gold is a pure gold, you will, if you can calculate or if you can measure the density of this object, then so the density should be exactly the density of pure gold. But if it's mixed by, let's say, some iron and gold or silver and gold, then the density of the object changes. Usually it's lighter because there are very few metal which have density higher than gold. If you want to mix some gold with some other metals which has higher density than gold, usually it doesn't happen because usually the metal which has higher density than gold is more expensive than gold. it's not smart to mixture some more expensive material into gold and claim this is a pure gold. So it's not smart. So if the smith want to play some tricks, usually he will mix some maybe silver or let's say copper or some other copper or some other material. But once he does this, the density of this object of the crown should be lighter. Now the key is, let's try to find out the density. So first of all, you have the weight of the crown. Can you calculate the density of the crown? The answer is yes. First, from the weight, we can calculate what? Mass. Weight equals to mass times g. If you know the weight, then you know the mass. And the goal is to calculate the density. Density equals to what? The mass over V. So now you know weight, you know mass. If you know the volume of the crown, you can calculate the density of the crown. So how to calculate or measure the volume of the crown? So Archimedes has a very smart way to calculate or measure the weight, the volume of the crown. He put it into the water, and then now if we look at, okay, let me switch my mouse into, okay, here. Now you have the weight, you have the tension, and then you can calculate the buoyant force. So from the buoyant force, you can calculate the displaced volume of water based on the equation of buoyant force. And the displaced volume of water equals to the volume of the crown. Then you can calculate the crown. Once you have the volume of crown and the weight of crown, you can calculate the density of crown. Now let's see the process. First, buoyant force equals to the weight subtracted by the tension, and you got the buoyant force. Once you have the buoyant force, now let's calculate the weight. Let's say the, what's this? V naught. It's a little bit messy here. Let's see. Okay, so this is a V naught is the volume of the crown, and the volume of crown equals to volume of displaced water. So volume of crown equals to m over rho, or weight over g, which is m, and then over rho. So this is the equation of the volume of crown. And then another way to involve volume is the buoyant force equals to rho Vg. This is what we just learned in this class. If we substitute V naught by the equation here, and then V naught over rho G is the volume of the crown and also the volume of displaced water. So rho Vg equals to FB. or buoyant force. And then G and G canceled, you will have this equation here. And from here, you know FB, you know weight, you also know rho fluid, which is the density of water. The only the only thing you don't know here is the density of rho naught, which is the density of your object, your crown. So rho naught equals to here, and then after you put all of the numbers into the equation, you can calculate it's here. The density is 17,000 kilogram per cubic meter. And it's a little bit lighter than pure gold. For pure gold, it's if I remember correctly, it's here. It's 19,000. So, but the crown is 17,000. That means the density is lighter. That means there's some mixtures of some lighter metal into the crown. So it's not pure gold. Okay, so this is the way of using buoyant force equation. Now let's see some, okay, float or sink. An object will float or sink depending on whether the fluid density is larger or smaller than the object's average density. If the densities are equal, the object is in static equilibrium and hence motionless. This is called neutral buoyancy. Of course, if the density of the object is higher than the fluid, it will sink. If the density of the object is lighter than the fluid, it will float. So here are all the examples. If the density of your object is greater than the weight should be greater than the buoyant force, it sinks. If the density of your object is smaller than density of fluid, then the buoyant force is greater than the weight. If you put it submerged in the liquid or in the fluid, it will go up, so it floats. In the third case, if the densities are all the same between your fluid and your object, it will stay or it will be static equilibrium in the liquid because the net force is zero. They cancel each other or they balance each other. They don't cancel, but they balance each other. Okay, if you understand this, now let's see this test. Which floating block is most dense? Can you make your judgment just based on the picture here? So A, B, C, there are 3 blocks. So which one is most dense? Please let me know your answer in the chat. Sorry, I gave you the answer. Sometimes my mouse is too sensitive. Okay, actually it's A. Why? Because if you compare the ratio of submerged part of the object, A has the largest ratio of submerged part over its whole part, or the volume of submerged and the volume of its whole object. So let's say maybe 80% of the object of A is submerged in water, but for B, it's only 40% of the volume is in the water. For C, half or 50% of the object C is in water. You can imagine the more or the higher ratio of this object is submerged in water, that means this density of the object is higher and getting closer to the water. If 100% of this object is submerged in water and it's still floating or in a static equilibrium, that means the density is the same as water. So B is the lightest and A is the heaviest in dense. Okay, now let's see another example, measuring the density of an unknown liquid. You need to determine the density of an unknown liquid. You notice the block floats in this liquid with 4.6 centimeter of the side of the block submerged. And when you put the block in water, it also floats, but there's a 5.8 centimeter submerged. So what's the density of the unknown liquid? So first of all, which liquid is more dense, do you think? When you put it in water, it's submerged more than this liquid. In this liquid, it's submerged less. So which has higher density, water or this unknown liquid? So most probably it's unknown liquid. Because a common sense is if the liquid is denser, then the same displaced volume of this liquid will generate more buoyant force, because rho GV, if V is the same, then because rho is higher, then it generates more buoyant force. That's why there's a phenomenon which is Dead Sea or Death Sea. People can float in the water because in that water, the density of the water is really high because there are too much salt in the water. So that's a common phenomenon. Let me show you something. Death Sea. Is it Death Sea or Dead Sea? So for Dead Sea, many of you may know this phenomenon because it's a sea of salt. The density of salt is really high. So the density of the water here is really high, so people can float. Let me see if you search it by the image, you can see people can easily float. A big ratio of the human body is out of the water. That's because of the density. So now let's go back to our question here. So if the unknown liquid just need a smaller part of the displaced volume to generate the buoyant force which balance the weight, that simply means this unknown liquid is denser than water. But how to quantitatively calculate it? The key is the weight is always the same, no matter in this liquid or in water for the object. If we write it down, that is, the connection is weight. The weight doesn't change. The weight equals to the buoyant force in water. Rho water, V water, which is the submerged part or immersed part of the water. V water times G. On the other side, the weight equals to rho unknown, or density of the unknown liquid, V unknown, the volume of the unknown liquid, and G. That's the key. So we want to calculate the rho unknown here. G is a constant. G can be canceled. If we know the ratio, and we know rho water, if we know the ratio, or if we know the V of unknown and V of water, then we can calculate the density of unknown. Even if we don't know the V, if we know the ratio of the height, it's also possible, because now if we look at this equation, we can convert this equation in this way. In this way, rho unknown equals to, let's say, V water over V unknown times rho water. From this equation, you can easily get this equation, right? And then V water equals to what? Let's say the area is A. The top area is A. And then the V equals to A times H water, because we want to calculate this part, the submerged or immersed part of the volume. So it's A times HW. What is the V unknown? The V unknown is this part, the submerged part. It equals to A times H unknown. So this is the VW, this is the V unknown times rho water. So A will be canceled. Then you get H water over H unknown times rho water. Then you can calculate the density, because you know HW, you know HU, you know rho water. So this is a way of calculating an unknown density of unknown liquid. So here's the same thing. It derives this equation. Finally, you get this equation. You just put the three numbers in, and you can get the number here, the density of your unknown liquid. Okay, boat and balloons. The hull of a boat is really a hollow shell. So the volume of water displaced by the shell is much larger than the volume of hull itself. So it can generate a much larger buoyant force, which is shown here, than the weight. The weight of the hull doesn't change no matter the hull is on the top or going down or going even deeper. The weight doesn't change. However, the buoyant force is getting greater and greater and greater, so it will float. The boat sinks until the weight of the displaced water exactly matches the boat's weight. It is then in static equilibrium floats. And balloons, the density of air is low, so the buoyant force from the air is negligible. So for example, when we're sitting here or we're standing, actually there's always a buoyant force on our body from the air, but it's too trivial compared to our weight. So usually we just ignore the buoyant force in the air. However, balloons cannot be filled with regular air because it could weigh the same amount as displaced air and therefore have no net upward force. But if you fill the balloon with a lighter density material like hot air, if the volume is big enough, then the buoyant force is great. It could be very strong. For a balloon to float, it must be filled with a gas that it has lower density than that of air. And then the buoyant force is greater than the weight, then it goes up, so the balloon can take you up. Okay, so that's pretty much everything we want to introduce in this class. Now let's do a simple test here. So 3 blocks are the same size. So which has the largest buoyant force? So can you make your choice in the chat? So which one do you think has the same, or which one do you think has the greater, larger buoyant force? Okay, so the answer is they have the same buoyant force. So no matter how heavy is a block, the buoyant force only matters or only depends on rho Vg, the density of liquid, the volume of displaced liquid, and G. G is a constant. The liquid is the density of liquid in this case is the same, and the volume is the same. So they have the same buoyant force. Okay, now 3 blocks have the same size, which is correct. Okay, which is correct about the scale readings? So please write your answer in the chat. Okay, so first of all, let's ask a question. If it's not in liquid, if we don't have liquid, then which one will read more? If it's not submerged in liquid, there's no buoyant force, then in that case, C will read more because C has greater or larger mass. Larger mass results in larger gravity or weight. And then you put them in water or liquid. Do they have the same buoyant force? The answer is yes, because they have the same size. So the buoyant force are the same. And then which one read largest number? It's still C, because C has largest weight. So the answer should be C is greater than A, and A is equal to B. Okay, so that's all for today's class. Do you have any questions? In next class, we're going to learn something about motions in fluid. If you don't have any questions, that's all for today. Thank you for coming to this class. I'll see you on next Monday. Bye-bye.